Good morning. Today's topic is the rigid body dynamics. We are going to discuss about torque, angular momentum, conservation of angular momentum, and rolling motion. First of all, what is torque? The turning effect is called torque. For example, in this body, this point is fixed and force is applied at this end. Fixed means loosely connected, hinged. This point is hinged. That means loosely connected, and force is applied at this end. Then the body can turn about this point. The turning effect is called torque, represented by the letter tau. Torque tau is equal to force into perpendicular distance between the line of action of force to the fixed point. This is called torque. So, SI unit is Newton meter. Dimensional formula m1 n2 p power minus 2. Torque, work, same dimensional formula. They are isodimensional quantities. But torque is a vector quantity, pseudo vector. How to represent torque in terms of vector means tau bar is equal to R bar cross F bar. This is the torque. Tau bar is equal to position vector cross force vector, R bar cross F bar. So tau is equal to force into perpendicular distance, or R bar cross F bar. R bar cross F bar. Here R means perpendicular distance. Next, suppose moment of couple. There are two forces acting on a body. The two forces are opposite in direction and they are acting at different points. Non-collinear forces, and one point in the body is fixed. The turning effect is known as moment of couple. So this one also represented by the tau. Moment of couple tau is equal to force into perpendicular distance between two forces. Perpendicular distance. This is the perpendicular distance. So force into perpendicular distance. This is called moment of couple because the two forces are acting. Okay, torque is a pseudo vector. It is a vector but pseudo vector. Vectors are two types na? Real vectors, pseudo vectors. Torque is a pseudo vector. And this is called moment of couple. Many examples we can see when opening the tap or tightening the wrench. Screw and nut we are tightening, so we can apply the torque. And driving, at the time of driving, we are using two forces at the two ends. Those are called non-collinear forces. The scooter can turn or car can turn. So those two forces are called moment of the pair of the forces, and the turning effect is called moment of couple, or that is also called torque. And we can write torque tau is equal to the rate of change of angular momentum. Tau is equal to dl by dt. The rate of change of angular momentum. In linear momentum, we have momentum p, mass into velocity. Angular momentum, circular motion, that is equal to I omega. This is called angular momentum L. But when angular momentum is changing, torque is required, and the rate of change of angular momentum is directly proportional to external torque. Just like the rate of change of momentum is directly proportional to force. F is equal to dp by dt, F is equal to ma. Like that, tau is equal to dl by dt. dl, change in angular momentum by time, that is nothing but a torque. The rate of change of angular momentum is called torque. Next topic about angular momentum. angular momentum. The moment of momentum is called angular momentum. The moment of momentum. Suppose one particle is there, mass m, velocity v, and it is moving with velocity v. So momentum is mv. P is equal to mv. About this point, this momentum is changing. The moment of momentum is called angular momentum. Mv into r. mvr. This is called angular momentum. L bar is equal to r bar cross p bar. R bar cross p bar. Angular momentum. The moment of momentum is called angular momentum, and we can write it as mvr. We can write it as m into omega by r. V is equal to r omega. Okay, r omega into r, that is equal to m r square omega. R square is I. We can write I omega. Angular momentum L is equal to I omega. One formula is there. Angular momentum L is equal to I omega or mvr. One formula. And the L bar is equal to r bar cross mv bar. Mv bar means t bar. Momentum, linear momentum. This is called angular momentum. The moment of momentum is called angular momentum. The moment of momentum is called angular momentum. SI unit of this one is kilogram meter square second power minus 1. Dimensional formula m1 l2 t power minus 1. m1 l2 t power minus 1 dimensional formula. The moment of momentum is called angular momentum. SI unit kg meter square second power minus 1. This is also pseudo vector. L bar is a pseudo vector. L bar is a pseudo vector. Cross product of any two real vectors is a pseudo vector. Cross product of two vectors is always a pseudo vector. Remember it. Okay. Next, law of conservation of angular momentum. Law of conservation of angular momentum. When there is no external torque, when torque is 0, angular momentum of a rotating body L is equal to I omega is equal to constant. When there is no torque, angular momentum remains constant. Even though moment of inertia, angular velocities are changing, but angular momentum remains constant. That is called law of conservation of angular momentum. That means omega is inversely proportional to I. Moment of inertia is more, angular velocity is less. Moment of inertia is less, angular velocity is more. So this is called law of conservation of angular momentum. If there is no torque, angular momentum constant. Example, when planets revolving around the sun, so this is the planet, distance is less, moment of inertia is less. Angular velocity will be more. Distance is more, moment of inertia is more, angular velocity is less. Here distance is less, moment of inertia is less, angular velocity will be more. Here moment of inertia more, angular velocity is less. When it is close to the sun, planet is close to the sun, distance is less, so moment of inertia is less, angular velocity will be more. But angular momentum remains constant. When planets revolving around the sun, angular momentum remains constant. Even for electrons also, when electrons revolving around the nucleus, their angular momentum is a constant, but that one depends on the orbit number, mvr. Angular momentum mvr is equal to I omega. Already we proved mvr is equal to mh by 2 pi for electrons. So angular momentum is multiples of h by 2 pi, and it depends on the orbit number. mvr. R is different for different orbits. That's why angular momentum also different. But in an orbit, angular momentum constant. In an orbit, angular momentum constant. That's why planets revolving around the sun and the electrons revolving around the nucleus, because no torque. Torque is zero. Angular momentum constant. So they are revolving with a constant angular momentum. Moment of inertia and angular velocity can change. If it is more, it is less. It is less, it is more. But angular momentum remains constant until the torque acting on it. Okay? So this is called conservation of angular momentum, law of conservation of angular momentum. And some more examples also we can see for this. That is when circus, when turntable, one table is rotating slowly, one person in the hands two dumbbells, he stand on the turntable, table is rotating, he also rotating. And if he holds, his hands are stretched initially. Suddenly if he folds his hands, his angular velocity can increase. His angular velocity can increase. What happens there? When he folded his hands, moment of inertia of the body decreases. Then automatically, moment of inertia of the system decreasing, angular velocity increases. Because the angular momentum constant. So the table can turn with more speed. In a diving also same principle. From the springboard, the person, diving person can oscillate like this. Then he has a certain angular velocity and moment of inertia. When he leaves the springboard, he jumped into water. Immediately he bent his body like this. His head comes to the legs. Then moment of inertia of the body decreasing. So automatically angular velocity increases. Then he can make turns in air and falls to the water with more angular velocity. So he is rotating with more angular velocity and falling to the water. For that they get marks. So that's why they can make more turns in the air. That is called somersaults. That is based on the conservation of angular momentum concept. Here torque is constant. No torque. Torque zero. No external torque. Torque is zero. Angular momentum constant. Angular momentum constant. Torque not constant. Torque zero. That's why angular momentum constant. Then I omega constant. I1 omega 1 is equal to I2 omega 2. There are I proportional to 1 by omega. I and omega inversely proportional. That is example for law of conservation of angular momentum. And one more topic, last topic is in this chapter, that is rolling motion. A body is rolling. This is called linear motion or sliding motion. Sliding. And this one is called rolling motion. Wheels of the car. Wheels of the car, rolling motion. Fan blades, rotatory motion. Rotatory motion means at the same place, fan blades are rotating. This is called rotatory motion. This is called linear motion. This is rolling motion. It has both linear motion and rotatory motion. That's why it is called rolling motion. Rolling motion is possible only circular shape bodies, sphere, disc, ring, cylinder, solid cylinder, hollow cylinder, solid sphere, hollow sphere, etc. But not possible for cube, cuboid. It is not possible. Rectangular plate, not possible. Okay, only ring, disc, sphere, cylinder. That means solid cylinder, hollow cylinder, solid sphere, hollow sphere, ring, disc. Total 6 bodies can roll. Possibility for rolling. Okay, a body is rolling. When body is rolling, its velocity of center of mass is V. Velocity of center of mass is V. And its kinetic energy known as kinetic energy in rolling motion. Kinetic energy of rolling body. Kinetic energy of the rolling body. Not rotational kinetic energy, that is different. So rotating body having kinetic energy, that is called rotational kinetic energy. Body moving in the straight line having linear motion and it has a kinetic energy. But when body rolling, it has a kinetic energy known as the kinetic energy of rolling body. It has two types of kinetic energy. One is translational kinetic energy. Second one, rotational kinetic energy. Translational kinetic energy and rotational kinetic energy. Translational kinetic energy means half I omega square, half mv square. Rotational kinetic energy means half I omega square. So it is a rigid body. It has moment of inertia I and angular velocity omega. It must be circular shape. So V is equal to R omega we know. Therefore that is equal to half mv square plus half moment of inertia of any rigid body formula mk square. General formula mk square. K is known as radius of gyration. And omega we can write v square by v by r. So omega square means v square by r square. Therefore kinetic energy of rolling body half mv square into 1 plus k square by r square. That is kinetic energy of rolling body. Let us assume k square by r square is beta. Let k square by r square is beta. Therefore that is half mv square into 1 plus beta. This is kinetic energy of rolling body. Kinetic energy of the rolling body. Half mv square into 1 plus beta. For any body rolling, point number 1. For rolling body, for a rolling body, fraction of Ke translational. That means what fraction? The kinetic energy is translational. That means half mv square by half mv square into 1 plus beta. That is 1 by 1 plus beta. That is a fraction of Ke translational. Percentage of Ke translational. Second point. Percentage of Ke translational. That is 1 by 1 plus beta into 100. Similarly, third point. Fraction of Ke rotational. Fraction of Ke rotational, that is equal to 1 minus 1 by 1 plus beta. That is beta by 1 plus beta. And the percentage of Ke rotational. Percentage of Ke rotational. That is beta by 1 plus beta into 100. This is the percentage of Ke rotational. So total 4 important concepts: fraction and percentage. Fraction of Ke translational, percentage of Ke translational. Fraction of Ke rotational, percentage of Ke rotational. 4 points you have to remember. Okay. Next, one more important point. A body is rolling. V is the velocity of center of mass. V is the velocity of the center of mass. And the body rolling. Radius is R, the body is rolling. then different particles having different velocities. At this place, V is velocity of this particle. At this place, it has a translational and center of mass velocity V, same for all particles, and V is equal to R omega, velocity along the tangent. Here one more velocity V is there. Net velocity at the bottom, V dash is 0. V dash is 0. And at this place, center of mass velocity V, tangential velocity V is equal to R omega, same direction. And here the net velocity 2V. And at this place, one velocity V, center of mass velocity, one is along tangent, so resultant velocity root 2V. Here also same, root 2V. Root 2V. Here and here root 2V, here 2V, here 0. At the bottom, for rolling body, net velocity of the particle at the time touching the ground is 0 and body is rolling. Okay? Next, what about beta values? Ring. I is equal to mr square is equal to mk square. K square by r square is beta. K square by r square, beta is equal to 1. Disk I is equal to mr square by 2 is equal to mk square. Therefore, mm cancel. K square by r square is beta is equal to 1 by 2. That means the quotient value is a beta. Solid sphere. Beta is equal to 2 by 5. Hollow sphere. Beta is equal to 2 by 3. 2 by 3. And the solid cylinder. Beta is equal to 1 by 2. Hollow cylinder. Beta is equal to 1. 1, 2, 3, 4, 5, 6 bodies only rolling. Possible. So beta values you can remember. Next, it is an inclined plane. A body is sliding. Sliding means coming like this. Here rolling. It is rolling like this. Then its acceleration A is equal to G sin theta only. Its acceleration A is equal to G sin theta. But for rolling body, acceleration is equal to G sin theta by 1 plus beta. This is the acceleration of rolling body. A is equal to G sin theta by 1 plus beta. Then the distance traveled L is equal to half A t square. T is equal to root of 2L by G sin theta. T is equal to root of 2L by G sin theta. Same way here, L is equal to half A t square. T is equal to root of 2L by G sin theta into 1 plus beta. This is the time taken. T to reach to the bottom. T is equal to 2L into 1 plus beta by G sin theta. And the final velocity on reaching to the bottom, V, T square minus U square is 2A is formula. U0, V is equal to root of 2 G sin theta into L. But for this in this case, final velocity of rolling body 2G sin theta into L by 1 plus beta. This is the velocity of a rolling body. Final velocity on reaching to the bottom. Here, velocity directly proportional to G sin theta, but here velocity proportional to G sin theta by 1 plus beta. So here important point is V proportional to 1 by root of 1 plus beta, T proportional to root of 1 plus beta. To compare the rolling bodies only, we have to take these 2 points. For rolling bodies, time taken and final velocity of reaching to the ground. So this is about rolling motion. Rolling motion. When body is rolling, its acceleration A is equal to g sin theta by 1 plus beta. One more point, to roll the body, the surface must have a little bit of friction. If it is frictionless, the body can slide. If there is friction, then only body can roll. The coefficient of friction, minimum coefficient of friction required to roll the body, mu is equal to tan theta into beta by 1 plus beta. This is a minimum coefficient of friction to roll a body. Minimum coefficient of friction required is mu is equal to tan theta into beta by 1 plus beta. Then only the body can roll, otherwise it can slide. Otherwise it can slide. Okay, so we can do some problems on this. Position vector 2i plus j plus k and force vector I minus 2j plus 3k. Calculate the torque about the point of force, about the origin. Calculate the torque about the origin. Calculate the torque. Torque toe bar is equal to r bar cross f bar. So take ijk, r bar quotients 2 1 1 2 1 1, f bar 1 minus 2 3. So I into bracket minus j into bracket plus k into bracket. That is equal to I into 3 minus 2 minus j into 6 minus 1 plus k into minus 4 minus 1. So that is equal to 5i, and this is also minus 5j minus 5k. That is the torque. Calculate the torque. Torque is equal to 5i minus 5j minus 5k. Torque acting on the body. Next one, to tilt a cylinder of weight W, radius is R, how much force is required? Its weight is W, height is H. Then to tilt the cylinder, torque in clockwise, torque in anti-clockwise equal. Therefore, W into R is equal to F into H. Therefore, F is equal to W into R by H, height of the cylinder. The force required to tilt the cylinder, to make the cylinder horizontal. There is a scale length 1 meter scale, weight is 80 grams, and at this end 10 grams is suspended, length is 1 meter. Find where it should be suspended by a thread such that the scale should be horizontal. The scale should be horizontal. So, let the tension is here P. Laws of parallel forces. Sum of downward forces, sum of upward forces equal. Therefore, tension T is equal to 10 plus 80, that is 90 gram weight. Gram weight is force, gram is mass, gram weight. Therefore, we need this distance from where it is suspended, x. About this point, torque in anti-clockwise, torque in clockwise equal. Torque in anti-clockwise means T into x is equal to 10 into 0 plus 80 into 50 centimeter, because it is 1 meter, weight is acting at the center, this is at 50 centimeter. Therefore, this is 0. Tension T is 90 into x is equal to 80 into 50. So, 0, 0 cancel. X is equal to 80 into 5 by 9. 80 into 5 divided by 9. 9 9 is 81, approximately 9. So, 45 centimeter. We are getting 45 centimeter approximately. Approximately 45 centimeter. So, if it is suspended, it should be horizontal. The scale should be horizontal. Okay, one important concept. If Earth mass m, radius r shrinks half of the size, radius become r by 2, suddenly Earth shrinks to half of the size without changing its mass. Mass remains the same. What will be the duration of the day? Present duration 24 hours. This is an important standard problem. Number 4. So it is suddenly shrinked. That means no torque is acting. Torque 0. Therefore, I1 omega 1 is equal to I2 omega 2. Moment of inertia of the earth 2 by 5 m r square omega 2 pi by capital T 24 hours is equal to, now it is shrinked. Mass remains the same 2 by 5 m, radius become half r by 2, r square by 4 into 2 pi by capital T2. 2 by 2 pi cancel, 2 by 5 m r square, 2 by 5 m r square cancel. We are getting 4 T2 is equal to 24 hours, T2 is equal to 6 hours. Now the duration of the day becomes 6 hours. Now the duration of the day becomes 6 hours. Okay. And what is the change? Is 18 hours. Change in duration is 18 hours. Number 5, a solid sphere is rolling on horizontal surface. Find the percentage of kinetic energy translational. Solid sphere rolling, we need percentage of Ke translational. So percentage of Ke translational means beta by 1 plus 1 by 1 plus beta into 100 per percentage of K translational, just now we discussed it. 1 by 1 plus beta into 100, that is 1 by 1 plus beta for solid sphere 2 by 5 into 100, that is equal to 7 by 5 by 7 into 100, that is 500 by 7. So 500 by 7 means how much percentage? 500 by 7. 7th 49, 10, 71, 3, 74 28, 71.4%. 71.4% is translational and remaining approximately 28.6% is rotational. Percentage is rotational. Like that problems we can do on rigid body dynamics. In this topic Mainly we covered torque, angular momentum, conservation of angular momentum, and rolling motion. Okay.